Hello and good afternoon to everyone. I hope everyone is doing well. Um, can you guys hear me?
Yes, yes.
Hello, yes.
Can you guys hear me?
Yes.
Okay, good, great. Okay, so I have uploaded the video of our previous lecture, and you can find it on Moodle. I probably will create a YouTube channel, and I'll put up the videos in that channel as well, because it's much easier to have everything in one place than to upload it on our Moodle server, which may or may not be available depending on how the situation of the servers are. I will be doing that probably within this week. So for now, we have the first part of what we covered recorded on Moodle. So please refer to that. Today, we will be studying the remaining part. Let me bring my slides. Okay. This, and this. So I believe you guys can see my slide right now. Okay, can you guys see my slide? Okay, good. Great. The only thing is now I cannot see how to use this. There it is, pen. Okay, before we continue, last time, I guess someone, Sultan maybe, had asked me about this knapsack problem. Sultan, are you there?
Yes, hello, I'm here.
Okay, great. So he had asked about what happens if we take the ratio of the value to the weight. And I said that that still wouldn't work if you are using the greedy approach. And just to give you a quick example, let me try to write it over here so you guys can. Oh, why is my pen not working over here? Okay. So assume that, so you remember the problem, right? 0-1 knapsack problem. Assume that our W is 50 kg, okay? So the capacity of your knapsack is 50 kg. And assume that I give you this table where we have 3 items, item 1, item 2, item 3. Okay, so these are your items. It's terrible to write using mouse. Item, okay? So we have 1, 2, 3 items, and over here we have their weights, weight of I. Oh, this is terrible. We have value, which is in dollars, say, okay, and this is their value. Let's extend this table. And in the end, we have the ratio. That means, sorry, not this. We have value to weight ratio, okay, WI. So the first item, say its weight is 10 kg, the second is 20, and the third is 30. All right. And say the value of the first item is $60. The second item is $100. And the last item is $120. So if you take the ratio of V to WI, 60 over 10, you would get 6 over here, 5 over here, and 4 over here, okay? So this is what Sultan was suggesting last time. Now, so if we use the greedy approach as we discussed, so I have 50 kg capacity. So the first thing that I would do is, first step is choose the item which has the maximum value to weight ratio, which would be item number 1. So I would put item number 1 in the bag. The weight is 10 kg, so that means I have remaining 40 kg. Now I have to fill that. So I'll go for the next item, which is item number 2, because it has a ratio of 5, which is the next greatest value. And I would take it, and that would be 20 kg. So this would reduce to 20 kg. So I can carry 20 more kgs, but this item number 3 weighs 30 kg, so it will not fit. And therefore I cannot carry it. So the maximum that I can carry would be item 1 and 2. And that would be a total weight of 30 and a total value of 60 plus 100, which is equal to $160. Am I right?
Yes.
Okay.
Yes.
But if you look at this, the best optimal solution would be if I would have taken item 2 and 3. So I would have left out 1. Item 2 would be 20. Item 3 would be 30 kg. So it will fill up the capacity of my bag. And the total worth would be 100 plus 120, which is equal to $20. Okay. So we see that if we use a greedy approach, we do not always get the optimal solution. The optimal solution over here is $220, but what we would get is $160. Okay. So this is to answer your question. Now let's move on. I will have to again do this. Mouse. Okay, oops, let's also destroy all this. Clear everything, clear all drawings. Okay. So we saw the example of the base station coverage as well, and we had this correction over here. This was equal to 1. Do you see my mouse, guys? Please let me know if something is wrong, okay? Because I'm using 3 screens and I don't know which one you are seeing right now, okay? Okay. So we saw this. Now we begin over here. Do we have any questions, first of all? Do we have any questions from our previous, where is Ainur? Ainur is here, Ainur, yes, okay, let me make you co-host in case I get disconnected or someone wants to get in the class, so maybe Ainur, you could let them in. Okay, so there are no questions, okay? Good, now we want to basically try to give a definition or what would be the format of an optimization problem. So the standard form, as we call it, of an optimization problem is, where's my drawing again? The standard form of a problem would be, you would always have minimize, okay? Some function, which is your objective function or cost function, okay? And subject to the set of constraints. And the constraints in the standard form would be either equality constraints or greater than equal to constraints. Okay, so keep that in mind. So if I ask you what is the standard form of an optimization problem, it would always be minimize some objective function, subject to a bunch of constraints where the constraints should either be equality or greater than equal to. So if I give you some optimization problem, which is not in this form, say it's maximize something subject to less than equal to something, that's when you have, and I ask you to convert it into the standard form, this is what you have to do. You have to know how to convert a maximize problem into a minimize and a less than equal to constraint to either equal to or greater than equal to constraint, okay? So this is known as a standard form, okay? And this x over here is actually a vector, so it can be of this form or it can be a single scalar value, okay? So depending on how the dimension that you're solving the problem, okay? And obviously we know that this x is the decision variables that we have seen so far in the previous examples. If you go back, sorry about this. Previous examples, if you go back and you see, like, the decision variable was this xi, which we had over here, and the previous one was, again, where is it? Again, the xi that we had over here. So they are the decision variables. And similarly, in the optimization problem, the xi's are the values that we have, and they are the decision variables. And we want to find those xi values that would satisfy not only the constraints, but also the objective function. Okay, so the solution, that means the x that we find, okay, it can be either binary solution or it can be any real or integer solution, these x values, okay? So any x value that satisfies all these constraints, okay, are called feasible solutions. Keep that in mind. So I'll show you an example and I'll tell you exactly what is our optimal solution and what is the difference between optimal solution and feasible solution. So problem, an optimization problem can have multiple solutions, okay? But what we want to do is we want to find the most optimal solution in this subset of feasible solutions, okay? So not all solutions are the optimal solutions, okay? They are feasible because they satisfy these constraints, okay? So they are satisfying these constraints, and if you plug in the value of x into f of x, you will get some value. But we have to find that feasible solution that when I plug it in f of x, it gives me the minimum value for f of x. Okay, that would be my optimal solution. Okay. Now, so basically, one very simple trick or the simplest way to convert any optimization problem into a standard form is, for example, if I give you maximize f of x, what you have to do is if you want to convert into minimize f of x, what you do is write minimize and you negate the function, the objective function. So when I say, so minimizing function f is equivalent to actually maximizing the negative of the function, okay? So if you have a maximize f of x and I say, okay, write it in standard form, what you have to do is just write, convert maximize into minimize, and f of x, you put minus f of x, that's it. So it's basically the same because it's a symmetric, right? So you're maximizing, when you negate the whole function, that means you're trying to find the opposite of what is required. If it's minimized, you're maximizing it. If it's maximized, you're minimizing it. Is it clear? Any questions?
No questions.
Good.
Yeah.
Questions.
You have a question? If anyone has a question, just please interrupt me and just ask me, okay? Because I don't want to stop and every time ask you. So if you do not understand something, just interrupt and just ask your question. Okay, so let's look at this example over here. I will give you like 2 minutes to look into this example. Basically, you know what it is. It's just objective function is a square, I'm sorry, a circle, and you have 2 constraints. So take a paper and pencil and try to actually plot it. It's a 2D plot. So on 2 dimension, try to plot it and see how it looks. And then I'll show you what is the feasible set of solutions and what would be the optimal solution. Or if you can find me the optimal solution, that would be great.
Can I ask?
Yes, sir.
When we write constraints, is it mandatory to write in form of greater or equal? Can we write
Well,
less or equal?
you can write it for now, but later on when we want to use a simplex method or we want to find the dual of a function, the methods require us to write it in some standard form, and then that would be our starting point in order to solve the problem. Okay, so for now there's no constraint, there's no restriction of whether you write less than or equal to. Okay, there's no problem with that. But at some point when I repeat that, okay, first we have to convert this problem into a standard form, then you should know what I mean by standard form. But that would be the starting point for solving a tabular method called simplex method and finding the dual. Okay.
Okay, thank you.
So anyone, any volunteer to solve this thing for me? Okay, I'll volunteer myself. Okay, so basically, this would be the graph. Okay, so we want to minimize a function x1 squared plus x2 squared. So basically, this is x1 axis. Let me use my pen 1 second. This is x1 axis, and this guy is x2 axis. Okay. And we have a circle which is starting from the middle. So this is just growing. So you have another layer here and you keep going, okay? The 2 lines or the 2 constraints are given over here. This x minus 1 greater than or equal to 0 is basically x1 greater than or equal to 1, which is this straight line over here. So at 1, any value greater than or equal to 1 is acceptable. So if you see this shaded means this is not acceptable. Every value in this direction after the line is part of our solution. That means every point here satisfies this constraint. And the second constraint is x2 minus 1 minus x1 squared greater than equal to 0, which basically is this quadratic function over here. And since it is, we can write this in the form of x2 greater than equal to x1 squared plus, it's written over here, x2 greater than equal to x1 squared plus 1. So every value in this direction over this quadratic line is our visible, satisfies this constraint, okay? Now we have to find that set of points that satisfy these two together. That means in this direction and this direction. So you see that this is the common area, that means between these two lines. You see every point that lies here satisfies this constraint as well as this constraint, okay? So this, all these points are known as our feasible solutions. So any point, so if I pick up this point, it would be our feasible, so it would be a feasible solution because it satisfies both the constraints, and I just put the value of x1, x2 into the objective function, and it will give me some value, okay? But our aim is to find the optimal point. That means since we want to minimize it, we have to find which point within this feasible set actually is the minimum. And that would be this black point over here, right? So if you plot it using MATLAB or Mathematica, I did this using Mathematica, you see that this would be the circles and this would be the point, which is this black point over here. And the value is x1 equal to 1, x2 equal to 2. That means if you see this is x1 and this is x2. So this point is the minimum of these. And therefore, it is a feasible solution, but it is the optimal feasible solution because compared to every other point, it is the minimum. It satisfies this minimum requirement of the objective function. Okay, so is it clear? Do you understand the difference between feasible solution and optimal solution?
Yes.
Okay,
yes.
So every optimal solution is a feasible solution, but every feasible solution need not be an optimal solution. Okay?
Okay.
Good. Any questions? No? Moving on.
Not yet.
I know there are people, I think, in the, are you able to admit them? Or it's only I can do that. Daniel, you can turn off your camera. Ainur, are you there? She's not there, I guess.
Sorry.
Why are you sorry? You don't have to be sorry, dear. Ainur, nope. Okay. Okay, I'm sorry, because there are people trying to get into the session and it distracts me every time I see the message. Okay, where were we? Okay, here we are. So in this course, we are going to look at the basic optimization techniques, okay? And these are the techniques that you'll be familiar with by the end of this course. That means you will be knowing what is bracketing methods, and bracketing methods are used for solving univariate optimization problems. That means you have only a single decision variable, or you have to find the optimal value of a single variable, okay? And it doesn't require finding the derivative. So it's just using back brackets. So I don't know whether you guys had a course on numerical methods or not, but in numerical methods, you should have seen bracketing methods. If not, we will see it in this course. Like the most common ones are the method of bisection, Fibonacci, and golden section search. So we'll be looking at each of them. Then we have interpolation methods where they require what we say, the derivative, finding the derivatives. There's another method, quadratic interpolation, which goes without the derivative, but it's an interpolation method. We'll see each of them as well. Then we have multivariate optimization. When it comes to multiple finding optimal vector, okay, like x1, x2, x3. We use the simplex method. As our friend asked, why do we need to understand the standard form? This is where we will see in the simplex method. And then where we do not need to find the derivative, it's just a tabular method. But if you need to use a method which uses a gradient, we have the steepest descent method, and then we also have methods which actually use the second derivatives of the function, objective function. And those are these three methods as seen over here. Then we will look at global optimization. And Okay, what is global optimization? I will explain it to you in the next slide. And how is it different from local optimization? So there are two methods, deterministic approach and stochastic approach. We will look at them, each of them separately in this course. And I guess that's it. You almost know everything. And then hopefully I'm trying to have a course on advanced numerical optimization where we'll actually be using convex optimization, and we'll be doing a bit more complicated, formulating more complicated problems. But for undergraduate, I think this is more than enough, okay? Okay, so let's start with some definitions. Now we have understood what an optimization formulation is, so it consists of many parts. One is the objective function. The thing is we have to specify whether we want to minimize or maximize the objective function. And the third thing is we have to have a bunch of constraints. Okay, so that makes up an optimization problem. Now, definition number one, feasible set. So I already explained to you what a feasible set is, right? So a feasible set is denoted by, let me bring my pen. Feasible set is denoted by omega, okay, the big omega, and it is all points, all x values such that it satisfies the constraints. You see over here, the constraints are greater than equal to or equality, okay? So all the points that satisfies the constraints and fall into this definition of a feasible set, okay? Now, in the feasible set omega, okay, we call the point x star, okay, as a global minimizer or a global minimum. Keep in mind the two terms, global and minimum. This is important. So we say x star is a global minimum if and only if, obviously, if x star is in the set, feasible set, okay? That's what we just saw in the previous example. And for every feasible point in the set omega, okay, the functional value of those points should be greater than or equal to the functional value of x star, okay? It means that, and I'm saying this is a global minimum. So we say that in the feasible set omega, there exists some point x star such that if I put that value in the function, the objective function, it would give me this. And I put every other feasible point in their objective function, it would give me this. And so every other point should have values either greater than f of x star or equal to f of x star, okay? So this is known as global minimum. Now, if we want to make it a bit more strict, so I can also have a more strict definition for a global minimum, and I call it the strict global minimizer or unique global minimum. I would like to use the term unique global minimum. It's the same as definition 2, except for the equality sign over here. That means there should exist only one point x star in the feasible set, which has the functional value which is the least as compared to every other feasible point. Hello?
You can hear.
You need to speak out loudly, dear. I can hardly hear you. Okay, I cannot hear you. If anyone can hear him, please tell me what he's trying to say.
No, we can't hear him.
Okay, so if you have any questions, maybe if you're not audible or you cannot you have problem with your mic, you can just type it in the chat box, and I will read it and I'll try to answer it verbally. Okay. Okay, so do you guys understand the difference between a global minimizer and a strict or unique global minimizer?
Not really. Can you please explain again?
Okay, so assume. Let me take you back to that example. Okay, let me clear everything. Clear all drawings. Okay, this example. So do you agree that this guy, this blue shaded area, is the feasible set omega? Everyone? Because it satisfies all these points inside, satisfy these two constraints, right? So this blue shaded area is our omega. Okay. Now, I would say that we have a global minimum, okay? That means every point in here, whether I take this point, and this point, okay? And let's take as well this point as well, okay? Now, all these points, they are feasible points. And if I find the f of these points, so if I say f of this point, that means the objective function, I put it in the objective function, f of this guy, f of this guy, and the f of this guy, okay? So we see over here that this value, the functional value of this point would be the minimum compared to the other 3 points. Am I right?
Yes.
Okay, so in this very case, we have a strict global minimum. That means there exists only one such point whose functional value is the least compared to every other point in this blue shaded area. Okay, now let me give you an example of where it is not strict. Okay, now let me draw you something over. I don't. Okay, let me try to pay attention. So assume that this is my xy. Okay, and say we have a function like this. Okay, so this is my x, y, and they have a function over here, which is my objective function f. Okay, is it clear? Now, in this graph, so and there are some constraints such that all these points above this function in this direction, okay, they are feasible. So this whole area is the omega. Okay, so assume that I have a point here, and I have a point here, and I have, I don't know, point here, and I have another point here. If I take the functional value of these points, okay, over here we see that I have 2 points, which assume that this line is a straight line. Okay, it's like this, and the functional values are the same at these 2 points. So I have a x star. Okay, so say, let's look at this point as x star. There exists an x star such that its functional value is less than every other point, which is true, or equal to any other point, which is a feasible point. So this x star is equal to the functional value of this other point. Okay, so but it is not a strict optimal solution. Okay, do you understand now?
Yes.
Yes, thank you.
Good, very good. Clear and mouse. So with this said, so we now know what's the difference between these 2 points. I'm sorry, these 2 definitions, definition 2 and definition 3. So strict means there is only one singular point, which is the global minimum. Okay, but with just global, or we call it also loose global minimum, it means that there may exist more than one global minimum, okay, with the same functional value. Now, now we have another definition. So now we are going to contrast global against local. Okay, so we know what a strict means. Okay, now we are going to look what global and local means. So when I say global, it means that in the entire, over the entire, for the entire function, okay, there exists one single global minimum point. Okay, that there exists one minimum point if I look at the whole entire function. Now, what does a local minimizer mean? Let me see if I can draw. Okay, I can draw here. So if this is my function, say I have some weird looking function like this, okay? In a local a local minimum point. So basically, if I want to ask you to find the local points or the minimum points, it would be 1 point would be here, 1 point would be here, okay? Now, this is my entire function. This is my objective function f, okay? The global minimum point for this function would be this, because this compared to every other, what we say, valley, this is called a valley, okay? Every other valley, this valley is the deepest. So this point would be having the minimum value of f, right? So this would be my global minimum. But if I only ask you, okay, I want you to find the minimum only up till this point of the function, not beyond that, okay? So I give you only a neighborhood of the function, and I say what would be the minimum point within this neighborhood. And this guy would be the local minimum, okay? So is it clear? So local minimum means within a given neighborhood. That means you do not have the entire information of the function, only you have the information of a given neighborhood. And you say within this neighborhood, what was the minimum value, which is this. But if I give you the entire function, then you would say, no, this is a local minimum, but the global minimum would be this. Sometimes it is good enough to find a local minimum rather than a global minimum, because all optimization problems, they take different running time to solve the problem. So if time is important to us, we would like say, okay, we are ready to trade off time with a local minimum. That means you do something, you compute it in a shorter time, but you give me a near optimal solution, if not the optimal solution. Хорошо?
Хорошо.
Good. Anyone, any question? We have someone in the chat. Maybe there'll be more than, yes, you can have more than one local minimum, definitely. And I'll show you examples in the next slides. You can have more than one global minimum. You can have more than one local minimum. Yes, that's true. Daniel. Okay, so now you know what a local minimum. So given a neighborhood, so the definition, the mathematical definition is here. So obviously it should be in the feasible set. And there should be a neighborhood. That means you say, okay, from this point to this point, within these 2 points of the function, or within this interval of the function, what is the local minimum? Okay, so it would be within some so all those points that lie within the neighborhood and are in the feasible set, find the local minimum, the functional value, the x value that would give you the minimum functional value. And again, this is the loose local minimum because you have the equality sign. For a strict local minimum, you just remove the equality sign. Okay, that's definition number 5. Now, this is very important. So like in the exam, you know me, these are the type of questions that I can ask you in a true and false. I can say true or false. Tell me, state true or false. A strict local minimum is always a weak local minimum. True or false? You have to think about it. So you're saying a strict local minimum is always a weak local minimum. Yes, because this is a subset of this, but this is not a subset of this. So that's true. Okay. So pay attention to these definitions. Is it clear?
Yes, it's clear.
Good.
I have two questions.
Yes, sir.
First, could you please explain the meaning of these 2 symbols, backslash and colon? What do they mean?
Backslash and okay. Let me bring my pen. Okay, so when I have to define something in mathematics, in set theory, if you remember, you have this. So you say that, let's say over here, for example, this, you have it over here as well. Okay, so I'm saying that for every x value that belongs to the feasible set, okay, such where is the backs? Okay, so this is such that. This column means such that, okay? This column means such that.
Such that, yes.
Such that f of x is greater than this for every, and this means and. Okay, so for every x that belongs to the set omega and the subsets, wait. No, sorry. This means there exists. This means there exists. Okay, so what I'm trying to say is that for every, so for example, if you look at definition 3, the definition of strict or unique global minimum, it seems that there exists, for every x that belongs in the feasible set, there exists some x star such that f of x is greater than f of x star. Okay?
Yes, now it's clear.
Good.
And the second question, I compare global minimizer and local minimizer, and why do we call it weak local minimizer? Why not just local minimizer?
Because it's the same as why we call a weak global minimizer and not weak. I mean, we should have the term weak over here as well. As I said, this is weak global minimizer or loose global minimizer. It's the same. Okay, so we can have in a given neighborhood. Okay, you can have more than one local minimum value. Okay, but if there is exactly one local minimum value, that's when it becomes a strict local minimizer.
Yes, thank you.
Okay, good. Thank you. Okay, no more questions, carry on. Good. Let's look at this example. Now, this is example of, again, this was supposed to be animated, but I don't know why it's not working. Anyways, suppose you have this guy, this is your optimization function. Okay, as you see, our friend had asked me, why don't we have less than equal to? See over here, only because of you, I have added less than equal to, just to let you know that it doesn't matter at this point. You can have a constraint where you have less than equal to as well. But when we want to write it in a standard form, so this basically obviously is not in a standard form, okay? Because this constraint is in less than equal to form, okay? But if we want to write it in a standard form, you have to somehow apply some techniques to convert this into greater than equal to, okay? Or equal to. But for now, let's stick to this. So this is the objective function. We plot it over here, and these are the constraints. So given these constraints, so this is saying that all the x values should be greater than 0, okay? And all the x values should be less than equal to 4 pi. So it should be greater than 0, less than equal to 4 pi, okay? So greater than 0, less than equal to 4 pi, okay? So all the values from this point to this point, and since it's equal to, including these 2 points, okay? Now what we want to do is, my question for you is, how many local minimums do we have over here? Can you tell me?
3.
Why 3?
Well, because in the given range of x, these 3 points are smaller than their neighborhood. The first, second and third are definitely lower, and the first is, we take it as minimum because we don't have anything on the left side, only the right side.
Good. Yes, so exactly. So there are 3 local minimum. Now you may ask me, but this is a global minimum. Again, this is a true and false statement. A local minimum, a local minimum. So a local minimum could, a global minimum could also be a local minimum. Okay. So over here, okay, there are 3 local points. So we see that there are 3 valleys. So the points at these valleys would be our local minimums. Okay, because we are looking at in the interval from 0 to 4 pi. Now, how many global minimums? So if I'm given the same interval 0 to 4 pi, among these 3 points, this point has the least functional value, and therefore this local minimum would also be my global minimum. Is it clear?
Yes.
Good. Moving on. Now we have a few more definitions. Let's see, what is this? This is, okay, definition of neighborhood. So if I've given you some point x naught on the x-axis, okay, and I'm telling you that, okay, I want to define the neighborhood of x naught. So, I'm sorry, for not in the x-axis, in the region, in the feasible set. So in the feasible set, you take some point x naught, one of the feasible points, okay, and I want to define a neighborhood for that point. So I define the neighborhood to be any delta value, okay, which such that all the points, the difference between x and x naught, so every point that lies within the distance, within the radius of delta from x naught, is called the neighborhood of x naught. So if I want to plot this, basically, this would mean that, so if this is my feasible region, and this is my x naught, and every point, so if I draw a circle around this, and this is the radius delta. So every other point within this radius of x naught is within the neighborhood of x naught. Is it clear? So that's defined as neighborhood. The next definition is differentiable. So you know that a function f of x is said to be differentiable if the first derivative of that function exists, okay? So you know what the first derivative means. So you take the first derivative with respect to x, and if there exists a derivative, we say that that function is differentiable. Now, a function is said to be continuously differentiable if the derivative of that function is also a continuous function. So we know that if you have a quadratic function, if you take the derivative, it would be a linear function. A linear function is continuous, therefore it is known as a continuously differentiable function. So f of x would be continuously differentiable, okay? A function f of x is said to be twice continuously differentiable if both f prime x and f double prime x are continuous. So if you take the first derivative and second derivative and you plotted both of them are some continuous line, then that function f of x would be twice continuously differentiable, okay? Now, continuity of a function. So what is the meaning of continuity? So we need to define this, and I'll explain it in a figure on the next slide. So we have a function f of x, okay, such that, so actually for every x in the feasible set, okay, there exists some function f of x. And if we take the difference of f of x and f of y, okay, and the limit such that x tends to y, that means x is approaching y, okay, and the difference is equal, and the limit of this is equal to 0. That means they are very close to each other, okay? And these points x and y, obviously they are in the feasible set. Then we say that the function f of x is continuous in the set omega. Okay, so that means if you just take a point, say for example, this is some function. So if I take this x and this point y, okay, so this is x, this is y, and they are, sorry, this is y, and they are in the feasible set omega. And if the difference between these two functions, okay, as x tends to, that means if x is moving towards y, okay, then the difference between this should be 0. That means there should be no gap between them. Then we say that this function is continuous. If there was a gap between them, that means if we had such a thing, so this is x and y, and there's no kind of connection between these 2 points, then this would not be a continuous function, all right? Now, sign keeping due to continuity. So based on the value of the x naught that you choose, okay, we have a definition of sign continuity. So we say that if it is a continuous function, then within a certain neighborhood, the sign of the functional value of that x and all the neighboring points would be the same. Now, this is the mathematical definition. Let me show you graphically what it means, okay? Mouse. Okay, so first let's look at some visual plots of what is a continuous function and a discontinuous function. Obviously, this is a continuous function because it doesn't break at any point. All the points are connected and they are continuous. Okay, oops, sorry. Okay, so this is a continuous function. This is at the discontinuous function. So as you see that at this point, this line is continuous and take up, it suddenly breaks. So the next point, that means if this is x and y, if you look at the definition over here, continuity definition, this will not hold, okay? Because the limit of this does not tend to 0, okay? Because this point is not connected to this point, and therefore this is not a continuous function. Or even over here, continuous, 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 and suddenly at this point, tuck, you go somewhere else and you come back. So this is again a discontinuous function. Is it clear?
Yes.
Good.
Oh,
So, tell me.
I'm just a bit confused, but I think I will get it eventually.
No, you tell me, ask me. I don't want you to be confused. Confusion is not a good state of mind. Ask me now. Don't worry. What happened?
To be clear, I don't have like exact question.
Okay, so if you just revise, I mean, continuous and discontinuous function, this is very obvious. Discontinuous means at no point over the function, there should be discontinuity, okay? So it should all be connected to each other. And if you go from one point to any other point within its neighborhood, okay? So there should be no gap between it. So if you take the limit should be equal to 0, okay? Now, sign maintaining due to continuity. So for example, if I'm looking at this point x naught, so this is my x naught point. Say here, let me use my pen 1 second. So say that this is the point x naught over here. Okay, and at this point, I take the functional value. And at some neighborhood of x naught, which is h naught, okay, so left and right of x naught, I take some equal distance. Radius h naught is a radius from x naught, okay? So within this neighborhood, we see that the sign is kept. So the sign of the function, okay, will always be positive, right? Is it true? It's maintained within this neighborhood. Correct?
Yes, that's correct.
That's very obvious. But now let's see over here if this is true or not. So if you have a discontinuous function as shown over here, so if this is my x naught, okay, I'm sorry, this point, this blue point over here is my x naught, so the functional value is x naught. And if I take the neighborhood of this guy, that means if I go h naught up and h naught, or in this case it's written h. So if I go h up and h down, you see that, I'm sorry, this point would be positive, because this point lies within the radius of h from x naught, and this point would be negative because it lies below the x axis. So this is a negative value. So the sign does not keep, so we cannot guarantee the sign continuity in discontinuous functions. That's what I'm trying to say, okay? Because you don't know where the next the discrete point of the discontinuous function would lie. Okay, that's why you cannot guarantee the sign keeping in a discontinuous function. But in a continuous function, given the value of x, you can always guarantee that this is true. Хорошо?
Okay.
And also keep in mind that you may ask me, okay, then what happens if like this function would go down here and then I take x to be here? So one neighborhood would be negative, one positive. To answer that question, the definition of sign keeping is that the function value at x point should be greater than 0. Okay, so we should consider only functions that are at x naught, okay, the functions that are positive. That's why over here we have drawn it to be positive above the x-axis. Okay, over here also it's above the x-axis, but due to discontinuity, it may go down, and therefore this point would not be true. Okay. But if it was continuous, I could have found some neighborhood for x naught such that all the points within that neighborhood would be having a functional value which is positive if it was continuous, right? So if it was a continuous line, I could take a smaller h naught value. Okay, so there definitely exists some neighborhood, but in this case, there exists no neighborhood, and therefore the sign cannot be guaranteed. True? Is it clear, guys? Anyone who has doubt, please ask me now. Okay. Now let's look at derivatives. Just to refresh your mind, what is a derivative? We have a function f of x, x cubed minus x, okay? And what we want to do is we take the derivative. So can someone tell me what's the derivative of x cubed minus x?
3x squared minus 1.
Good. Thank you. So now this is a cubic function, right? So it has x cubed, so order 3. So let's plot it. So when you plot this x cubed minus x, it would look like this, okay? And these black lines that you see over here, do you see the black lines at some points, like this line, this black line, this black line, this black line? So these are the slopes, you know the definition, right? Slopes. So now what happens if I take these slopes, okay? And I just draw the slopes. So basically this line is this one here. This line is this one here. This line is this here, the horizontal line, and so forth. I just take the slopes and I draw it. So this was my x-axis and this was my y-axis, okay? So now I'm drawing the slopes. Now I want you to tell me, what does the slope tell me about the function? From the slopes, what can you tell me about the function, behavior of the function?
How fast it's rising or falling?
How fast it is rising and falling, or even to be more abstract, whether it is rising or whether it is falling, right? Whether the function is increasing or decreasing. So over here, when I see the slope is going up, so obviously I know this is x and y axis. So obviously the function at this point would be increasing. As we see over here, it's going up. At here we see, yes, it's still increasing, but the slope is decreasing compared to the first one. So it is slowly trying to become horizontal. At some point we see, yes, it becomes horizontal. So the slope is equal to 0 at this point, right? And then we see, oops, it goes down. So now the function is decreasing at some point. And then again, it becomes horizontal, then increasing and increasing. So we can say that at some point, there is either, so at 2 points, this point and this point, okay, the slope becomes 0. Am I right? So I can say either of these points could be either a minimum point or a maximum point. Am I right?
Yes.
So if you look at this function, you can tell me like, okay, this is a local maximum point. This is a local minimum point. Okay, because this function, we don't know how, I mean, the scope or the range of the values. So within this context, we have one peak and one valley. So when we get a 0 slope, it means that it is either a maximum point or a minimum point. But this is not, the statement that I'm telling you is not 100% true, and I'll tell you why in the next slides, okay? But I'm just trying to take it step by step and to explain to you from the derivative why we need the derivative in order to understand or actually find the optimal point in a function, okay? So everyone understand what the 0 signify and what the plus and minus signify, right? So this guy is a minus and these two are plus because they are increasing, and this guy, these two are 0. Now let's move on. Mouse. So now just to summarize what we just saw, I can say that if I see a positive derivative, it means that the function is increasing. Negative derivative means it's decreasing. If it's 0, it means that at some point we are seeing some special behavior, okay? Now it could have a local maximum point or a local minimum point. But there's a third scenario also that may occur. And the third scenario is that it could be neither of this. It could be neither a local minimum or a local maximum, but instead it could be a stationary point. Now, what is a stationary point? Just to give you a quick idea of a stationary point, say you have such a function. Okay, so this point over here, you see that the slope is 0, but we do not know whether it's a local minimum or a local maximum, right?
Yes.
Is it clear? So this point, we do have no idea. We know only the slope is 0, but every 0 slope doesn't mean that it's a local minimum or maximum. It could also be something known as a stationary point. Okay, so basically this is known as a stationary point. So with the first derivative, we know that something special is happening, okay? It could be a local minimum or local optimal point, okay? But we are not sure yet. So we need to have some more tests, to do some more further tests to verify whether we are right or not, okay? So this is known as stationary point. So there are 3 possible outcomes of a 0 slope, local minimum, local maximum, or a stationary point. Keep that in mind. Good. Example, I want you guys to take 2 minutes to read this and to we'll try to solve this using what we have seen so far. So read the problem statement. Okay, I guess it's very simple. So what we have over here is we have we are given that I don't know, the perimeter of some rectangle is 100 centimeters. Okay, let me use my pen. We want to find that rectangle, okay, whose perimeter is 100 centimeters, but it has the largest area among all possible rectangles. So you know that given the perimeter, you can have different rectangles of different areas. We want to find that rectangle which has the largest area. So basically what you have to do is you have to relate the perimeter of a rectangle to the area of a rectangle. Am I clear? Is it clear?
Yes.
So you know what a perimeter is, right? The sum of these lines, the borders, okay? So 2x plus 2y should be equal to 100, which is this equation. And obviously we have the area of this, if we say this length is x and the height is y, so x and y, which we denote by a, we want to maximize this. Rasha? So maximize area such that the perimeter is what? Equal to 100. Now, we have this equation, we have x and y, so writing them in terms of x and y. So what I can do is I can plug in this value of y into the area. So in place of y, I write everything in terms of y and plug in here. So my area would be a function in terms of x. So this basically would be my f of x function that we have seen so far, the objective function. So we are trying to derive the objective function, right? So which we want to maximize. So we want to maximize a of x, which is 50x minus x squared. Harasha? Good. Any questions? Please ask me. Okay, next. So what we do is we have a of x. Let me use my pen again. So a of x, as you saw, it was a quadratic function. So basically, if you plotted, this is how it would look, this function over here, this graph over here. And if you take the derivative would be a line, which is shown over here, okay? Now, let's look at the graph over here. So if you look over here, so we see that this point is increasing, and then suddenly at some point it starts decreasing. Okay, so this is my function. Okay, so we want to find the value of a, which is the maximum. That means a. So for example, I'm sorry. I'm terrible using my mouse. So this point is basically the maximum area, right? A of x, because this y-axis is a of x. Is it clear, guys?
Yes.
So this is the largest area that the rectangle can have with a perimeter of 100 centimeters. Okay, so if we draw this answer would be, I think, 25. Okay. Now, if you look at the derivative, that means this function, which is the line drawn over here, okay, and you see at x equal to 25, it crosses the x-axis, so that means it becomes 0. So the derivative becomes 0, which is basically this point, because at this point the slope is 0, right? So at this point, the slope becomes 0, okay? Now, so what we have seen so far is if the x-axis, if the value of x is less than or equal to 25, okay, it means that means this area, the function is increasing. So all these values are increasing. These points are increasing up till here. So after 25, everything is decreasing. The slope is decreasing, right? So at x is equal to 25, the transition happens. That means this. So this point actually divides this from this. So everything in this area is decreasing slope. Everything in this area is increasing slope, right? So therefore, at this point, we see that we find the value of x, which is equal to 25, and therefore so if we plug in x into our previous example, what would be the value of y? What would be the value of y?
25.
Yes, so basically it should be a square. Am I right?
Yes.
Good. Is it clear?
Professor, why there's a point on 20 point on x?
No. This point is just to compare x. I'm sorry, the point with the optimal point. Okay, so I'm saying that every point that is less than x, for example, dot, okay, would be having a slope, increasing slope. Okay, would be having an increasing slope and would lie in this area. So you see over here also I've shown x over here. So let me use my point. So that point would be in this area, right? But it would not be the optimal point. Okay, that's just for comparing with the optimal point.
Okay.
Okay, good. Okay, now let's revisit the equation, the example that we saw earlier, the x cubed minus x example, and we plot its derivative. So this was the example. So this basically is the function f of x, and this is the derivative of f of x, which is equal to 3x squared minus 1. Okay. Now again, over here, So what I'm trying to tell you is that this function, as you see over here, can you tell me whether, okay, what is this point? Is it a local minimum or max? Not this point, sorry, this point. Is it a maximum, local maximum or local minimum?
Local maximum.
Okay. How about this point?
Local minimum.
How about this point?
Stationary point.
Well,
Stationary
it's you
Just
cannot say
measure.
anything about this point. It's not stationary. Why would you say stationary?
Stationary, but point of change.
Stationary means the slope should be equal to 0. Is the slope equal to 0?
No.
No, so definitely it's not a stationary point. So stationary point is a point at which the derivative, if you take the derivative at this point, it should be equal to 0, and it is equal to 0. You see that? So this is not a stationary point, okay?
Yeah. Okay.
Hello? Guys, can you hear me?
Yes.
Yes. Yes.
Yes.
Okay, good. Now, we saw the first derivative. So basically, the first derivative tells us whether the function is increasing or decreasing. Now, we look at the second derivative. And I told you at some points, where even the first, in knowing, having the information of the first derivative does not help much. So we need to do some more investigation. Now, let's look at what information the second derivative tells us. So, of course, I told you what twice the differentiable function means. That means if you differentiate the function 2 times, we should still be having a continuous function. If it's a continuous function, then it's called twice continuously differentiable. Okay. Now let's. Okay, so now we had, so taking the same example, the same function, x cubed minus x, the first derivative would be 3x squared minus 1. The second derivative would be 6x, right? So if you take the second derivative of this guy, it will give you 6x, okay? So we see that there exists a local maximum, minus 1.3. Okay, so if the second derivative, this is important, if the second derivative of a function is negative, so you find the second derivative at a particular point and you plug in that value and you check whether it's positive or negative. If it's negative, okay, the derivative of f is increasing. So that means that if you want to know that x is a critical point, that means, so if x is a critical point, that means the first derivative, okay, of that function is a slope, which is 0. That's a critical point. So now critical points means it's either local minimum, local maximum, or stationary. Okay, that's what we mean by a critical point. Now, if x naught is a critical point, so we have taken the first derivative and we saw that the slope is equal to 0. So, but we are not sure yet whether it is stationary or non-stationary. So to confirm that, if we take the second derivative at that point, and if it is less than 0, then that point is a local maximum. If it is greater than 0, then it is a local minimum. That's it. Is it clear?
Yes.
Yes.
Good. Now the question is, well, let me keep it for later on. For now, let's stick to that. So I'll repeat what I just said. If you have a critical point, that means we have found that the first derivative of the function is the slope is 0. Okay, and we want to see whether this point is a maximum, local minimum, local maximum, or stationary. So to do that, we need one more step of investigation, and that is we take the second derivative of the function at that point. If it is less than 0, then it is a maximum. If it is greater than 0, it is a minimum. Okay.
If it's 0.
Well, if it's 0, you tell me what is left.
Stationary.
Good. That's what I wanted to keep it for. I mean, I wanted to put it in a quiz, but you understood. So good. You should pay attention. Okay. So these are the things that you need to know. So as our friend said, if it's equal to 0, it would be a stationary point, and that helps us confirm our analysis. We can understand. Okay, so when we well, this is not important. You can read this. Concave up, concave down, and it's well, it's telling you how do we know that when we take the second derivative, and how does the second derivative being greater than 0 tell us whether it is actually a local minimum, and how does it being less than 0 tell us it's a local maximum? Okay, so this is the slide. It depends on how you look at the, what is this called? The slopes of the tangents at those points. Okay, and if it's in this direction, that means it's a concave up. That means it's like this, and therefore it will be a minimum point because it's going like this, right? And if it is in this direction, that means it's going up. It will be a concave down. That means it's going up, and therefore it would be a local maximum. Okay, and as our friend said, if it will be the derivative is equal to 0 at this point, it's called an inflection point. That means it was actually a stationary point, and so it is not optimal. Okay, so that is on this slide. Is it clear? So if the second derivative is negative, the slope of the tangents would be decreasing, as you see over here. You see it's decreasing, and therefore when it's decreasing, that means that this, so if at these points you take the tangents, so these are tangents at point -2, -1, 0, 1, 2, and you connect the interpolate it, you would get such a thing. So you would see that the line is going up, and then slowly it is concaving down. That means at some point it's going to decrease. Oh, sorry, my pen, right? So this, if you carry on with this, at some point this is going to decrease, and therefore there will be some point over here, which would be my maximum point. Okay, similarly, for the previous case, we have this same definition. So if you connect if you kind of interpolate at the tangent point, you see that this is going down, and this would be some local minimum for the second derivative greater than 0. Okay, clear? This is basic, something that you should have learned in what we say, calculus and your geometry and all that stuff. This is nothing to be worried about. All you have to take away from here is that if you find the slope is equal to 0, you cannot confirm whether it's an optimal point or a stationary point. You have to do a further test, and the further test is to take the second derivative. And if the second derivative is less than 0 at that particular point, it's a local maximum. If it's greater than 0, it's a local minimum. If it's equal to 0, it's an inflection point. That means it is, you cannot say anything about that point, okay?
Can you please clarify what those red lines mean?
These red lines?
Yes.
Okay, so
just,
do you know what a tangent is?
Yes, I do.
A tangent is a line that touches a line at some single point, okay? So if I'm drawing, the tangents, not the tangent, the slopes of the tangents, okay, at these points, okay? So it would be basically, so at -2, so if you take this, where is that function? This function, x cubed minus x, okay? And now you draw me the tangents of this. So this is the first derivative, right? And you're drawing the tangent. So you see -2, -1, and 0, 1, 2, okay? So now you draw me the tangents at these points, okay? So that's what I'm doing. I'm decreasing it, and this is increasing. And therefore, I see this curve coming down, right? So I can say that this would be a local minimum. Am I right?
Yes.
Similarly, this would be a local maximum. So the tangents are increasing, and then suddenly, so if you draw the tangent, this will be, let me draw a tangent for you. Let me also use the same color. So for example, at point -2, this would be this tangent, this one. Then you would have, say at -1, another tangent like this. And you see that this tangent is, as you see, decreasing, right? So at some point -2, you see this is decreasing, and therefore you know that it's going up, and therefore there would be a local maximum up here. Got it?
Yes, thank you.
Good. Okay. I guess our time is up, but let me see how much is left. Okay, so this is an example. I want you guys to work it out. This is for you to work it out. In the next section, I'll ask you the solution to this. I'll ask someone randomly. So this is your function. tell me how many local maxima minima are there. What are the zeros of the derivative? That means what are the, at what points are the derivative, are the slopes equal to 0 or the derivative equal to 0? And how do the near the 0 determine whether, okay, now how do you find whether that point is a local maxima or minima? So you have to use the second derivative test. And the last question is, why is there one point which is a 0 of the derivative yet not a local minima or maxima? So you have to answer that question. So there are 4 questions, answer it, and next time I'll ask each of you randomly, okay? So that's it for this section. If you have any
Professor?
questions, yes, sir.
Can you go back to the where's function x cubed minus x? Yeah, that's one. The point where x is 0. Their second derivative is 0, so it's inflection point, yes?
This point?
One. Yes.
So at this point, if you take the derivative would be this point, right?
But second derivative is 0.
So the second derivative of this is 3x. The second derivative will be 6x, right? 6x would be 0, so it would be 0. So this would be an inflection point, yes.
But it's not stationary.
It's not stationary, no.
No, okay.
This is a stationary point. This is not a stationary point, but it is an inflection point. So you should always, so unless and until you don't take the second derivative test, you cannot say anything about whether it's increasing or decreasing, okay?
Okay, thank you.
It's very obvious. If you look at, I mean, all you have to pay attention, because we are trying to find the local minima maxima of the actual function f of x, okay? We are not finding the local min, because this is what many students confuse it with. They think that we are trying to find a local minima maxima of its derivatives, first or second derivative. That's not what we are doing. We are plotting the second and first and second derivatives in order to help us determine what kind of point this is. Okay, well, this is an easy thing, because this is a 2-dimensional, you have 2 values over here. I mean, 2-dimensional plot. Okay, you have f of x and y, and therefore you can plot it even if you're not sure. But what happens if you have a multi-dimensional case, okay, where there are x is a vector and not a scalar value? Okay, in that case, you cannot plot it. So you should be able to use this derivative test in order to verify it, right?
Yes.
Okay, good. Are we done? Any questions?
Can you go back to the very first example?
Slide number, please. Tell me when to stop.
Okay, back. Yes, this one. X is equal to 5. Do I understand it correctly? In the graph, we don't have an upper limit.
We do not have an upper limit, no. This keeps on continuing up.
But why did we highlight 5?
We highlighted 5 because the value over here is 5. This value is 5. Say 4.6. So the function, this 5 is, thank you, baby. This 5 is the functional value of this. So if you plug in 1 and 2 in this objective function, you get 5.
No, I see. Yes, thank you.
Хорошо?
Хорошо.
Good. So the last slide is for you guys to work it out, and I want the answer in our next session, which will be on Tuesday. Thank you very much, and take care of yourselves. See you and